This is Kristóf Fenyvesi, born in '79, Hungarian origin. He is a researcher of STEAM, sciences, technology, engineering, arts, and mathematics, trans and multidisciplinary learning and contemporary culture studies at the Finnish Institute for Educational Research, University in Finland, Jyväskylä. He is a member of Research Group for Innovative Learning Environments and the Research Group for Education Assessment and Learning. Fenyvesi is Community Events Director of the Bridges organization, the world's largest education community for the mathematics and the arts. He has been the editor of the annual Bridges Conferences Workshop paper track and coordinator of the Bridges Public Day. It's a lot of story to say about him. His main areas of research are mathematics and art connections in learning, STEAM education, inquiry-based, cooperative, playful, and experience-oriented approaches in mathematics education, problem solving in mathematics in science and art education, connecting hands-on activities and digital modeling in mathematics, science, art, and design education, science and art connections in learning, phenomenon-based, multi and transdisciplinary learning and co-teaching, and so on and so on. We heard about his activity also last week, integrated in this very large researching project. His articles were published and among others in the Notice of American Mathematical Society, Focus News Magazine of the Mathematical Association of America, Nexus Network, and so on. I'm very happy to invite you, Kristóf, to present your work. Thank you very much.
Thank you so much for Violeta, Dinescu, for this heartful introduction. And I'm really glad that you don't took it longer, because we need time also for the reason why we are here. So thanks a lot. You are very kind. And thanks a lot for Ioannis Liritzis for organizing this meeting together with Professor Dinescu. And thanks a lot for our president, Klaus Mainzer, for supporting this effort, because it leads us back to the beginning of the spirit of the academia, I think, because we are all lovers of art and sciences, and also the great tradition of having symposiums and celebrate our passions in this free format, also in these evening hours, in this nocturnal way a little bit. So I'm really glad to be here. And I'm also really happy to hear that my colleague, another academician, Professor Lavica, has been already a very successful speaker here. And you heard already a lot about those projects, which I will give maybe a little bit more insight in a little bit of those in this format of this short talk tonight. So let me share my screen. You can see that the title of the talk is a little bit complex, cognitive development through experiencing mathematical connections in art and design. So many of you can think that, okay, how this all comes together, but it comes together very naturally. And I hope that you will be convinced about this natural connection and even this playful connection for the end of this short talk. So as Professor Dinescu already presented, that I'm member of this Innovative Learning Environments research group. And in this research group, we are very interested in the physical environment of learning, of course, as you can assume, but also the mental, the social environment of learning and the process of learning itself. So how this interplay between physical environment, social environment, and also neuropsychological processes are coming together in this complex relationship. That's what we are looking for in these projects. You can see many of these projects logos are represented on this page. Later I will share a page where you can take a closer look at these projects. So to step close to the topic for tonight, I would like to return a great mathematician and mathematical didactic specialist, psychologist as well, Zoltán Paul Dienes, who, or if I can say in Hungarian, Dienes, who had a fantastic book already in the 60s. It's called Building Up Mathematics. And as you can see, the book original preface was written by Sir Herbert Reed, who really reformed art history. So a fantastic art historian wrote a preface for a book of mathematics and a book of cognitive perspective on mathematics, how to build up mathematics literally, how children can use a lot of manipulatives to literally build up mathematical concepts. So this is somehow the basics of the book. But how come that an art historian write a preface for this? You can assume also in the same time a very technical book, but it's not a technical book at all when you look at this classroom from the 1960s. This is one of Dienes' natural area, his territory sort of, where he allowed and supported children to contribute to create their own environment. And you can see already in this photo that how many different kind of learning opportunities are not, I won't say provided, because many of these opportunities are created by these children. And to find the teacher in this group, you can be a little bit challenged to spot her out, because she's one of those learners who are immersed in these various activities in this very inspiring environment. And if I tell you that these children here are not only learning, but doing and making mathematics here, that's something very significant, I would say, looking at this picture. And let's jump in time like 50 years later. This is Cambridge University's primary school, where my colleagues from Finland, Mrs. Sinnemäki from Finland, and and my colleagues are doing very similar activities in a little bit less colorful environment than you have seen from the 60s. And this school is regarded as one of the most innovative primary school around the world. And you can see even the difference, that how far we are from these ideas still. So still a way to go forward to complete this dream, what Dienes helped us to dream together. And if you can see this other picture, you can see that it's a very traditional classroom here, but here is something happening. Probably a game is folding out, because Dienes was very famous to create a game from anything and create a mathematical game from anything. And you can see this scientific imagery on the walls, but these are also presented as art. So you can see a lot of connections to contemporary art as well. And another jump in time, another experience workshop event, we have this STEAM community where we try to do this learning by doing activities with children through movement, through dance, as we also learned from Dienes. Another picture from a very different environment, again, jumping in space to in geography in New Guinea, where Dienes was sent as an inspector of pedagogy in the rural schools through swamps and very challenging natural circumstances, where the school was launched in local pubs. Yes, in pubs. You can see these empty glass bottles here. So very uneducative environment, if you say so, but you can see what's unfolding on the table and what kind of content is filling this room through playing with these children. And another switch in space, to and time. This is us, our group in South Africa, and you might not recognize because the children are wearing uniforms, but this is a school and the center in a very, very poor area. And these children are all coming from very challenged families and very challenged circumstances, but you can see the joy of mathematics shared here. And to explain a bit the background, so we try to develop different competencies, different skills according also the Finnish core curriculum. You can see the main competence areas what we try to focus through these events. So you can see, for example, thinking and learning to learn. So how we can reflect on the learning process itself and how we can learn different techniques to learn new things. This is one important mission for the school and one important mission for an academy to support lifelong learning, right? So how to raise brain awareness, how the brain is working, how the learning processes are happening, and actually mathematics and mathematical activities and these games and then these creative activities have sort of direct access to this level of metacognitive development as well. So this is what we are looking for in these activities. And as you saw in DNS, multiple diverse spaces, this is also multiple creativities need to be recognized and need to be nurtured with these children. And when I say this, it's really, okay, maybe you don't see in the slide, but we can talk about cultural creativity, transdisciplinary creativity, even digital creativity, collective creativity, individual creativity through partnerships. So we should recognize also that the schools, as we see it many times, even the most advanced school can be still very limited to appreciate those many kinds of creativities what we are developing throughout our lifestyle. And it's also interesting to recognize the teacher in the role that how can one facilitate these different creativities, how can one channel into creative processes in these diverse creativities, and how to create a sort of a creative ecology in the classroom. So we can see this unfolded, of course, in the famous Finnish educational venues in Finnish schools. This is one school, some corner from the place where I'm now. It's my friend's Jukka Sinnemäki's classroom, where you can see a lot of sport equipment installed in the learning space and also many other things, but it's really a space for active learning where the children can really be a complexity of mind and body at the same time, and also learning mathematics, which we can regard traditionally as the labor of the mind, the intellectual highest level intellectual activities, one of those. But of course, it has also historically and neuropsychologically many bodily connections if we go deep also in the origin of mathematical concepts as well. So this is important to recognize. So this is what we are looking for, this so-called STEAM integration, which is the integration between science, technology, engineering, arts, and mathematics. But we could say many other fields as well. This is just a useful acronym what we use in the International Educational Glossary. So, but it can involve many things, and the emphasis is probably on the collaborative problem solving and the community of learning and recognizing different fields of inquiry in the learning process. We have several inspirations here in the background. There could be many talks, and there are many talks, each of them, and how we can connect to them in these processes. So I better not go into that right now, but I would like to invite you to celebrate because it's the 150th anniversary of a very famous European math artist, Piet Mondrian. Was a Dutch painter. You all know his very characteristic compositions, and you can see also the direct connection, for example, with Euclid. This is a colorful edition of Euclid's Elements, a very famous edition. Many of you know this edition, and you can see also that how this imagery and how these sources are combined also in contemporary design, as Mondrian inspired designers as well. And we all know also that for Mondrian, it was not only a visual adventure and not only an intellectual adventure, but also a spiritual adventure to go and discover this visual culture what he created in a very characteristic format. So there is also even transcendental message as he intended, but of course our understanding is much broader than it was in his age or in his interpretation. And how it comes to gaming, of course, when you are in a Mondrian exhibition and you start to enjoy these works, your brain probably starts to play a game, starts to recognize this logic, what is in these paintings. And indeed, there is a game called Mondrian Blocks. Here is a game. It's not a Mondrian work, but you can see the connection between the game and the work here. And you can also see that how Mondrian Blocks is played in one Finnish classroom. And also you can see that how it helps concentration and how you can use it to help children to get into the flow of problem solving. When we have many sources of inspiration around us, many stimulations around us, it's very important that children can learn how to silently, or not silently, but focused way concentrate to certain problems to solve. So this is what was recognized also. Professor László Mérő, a psychologist and mathematician, when he actually discovered this puzzle, when he created a challenge for an escape room. So you can see the Lego prototype of the first game, and it's based on this very simple system, this very simple logic. When he recognized that, look, these are coming together as 64 squares, and there are many puzzles are hidden in this setting. For example, if you take these objects as blocked, that you are not supposed to move them, then how you can feel the plate, the board with the different elements. That's a challenge for this game. That was one of the basis of this game, and he published in a book actually, and in several books also. He presented this kind of mind-boggling puzzles, and there was Imre Kökényesi, also was working with Rubik Ernő in the Rubik studio, who actually made the connection between this puzzle and the Mondrian's paintings, and he designed the product as it is, as a game. So you can see these different color combinations. It's won a lot of awards, and also it was recognized as a developmental toolkit. So not only as a game, but something which can help children to think on a combinatorial way and visual combinations and manipulations and using the brain and the hand at the same time. This is a very important connection. And as you can see, that's how the game is played. You take a challenge card, then you arrange the black pieces as the challenge card show to you. You cannot move anymore the black pieces, but you need to find out what's the way to fill up the board with the rest of the pieces. So there is only one solution to each challenge. But interestingly, more and more games are coming even right now, even after this game was released. So there were also many hidden new game modes are appearing. For example, this two-player game, this is a classic NIM game where there are no fixed elements anymore, but the person who cannot put any more to the board any elements, that lost the round, and then the empty pieces are counted, and that becomes the point of the other player. And then after 2 rounds, you might see if there is a balance between them or one of the player won the match. So there is even this two-player game appeared from the same system. So that's also an interesting aspect of working with systems, that new and new characteristics appear throughout their lifetime, and this can be also implemented as games if you have the intention to introduce, for example, educative games for these systems, from these systems. Okay, and then this also inspired us to think about this system as a cognitive universe, and we had a hypothesis that this game could be also a measurement and development tool in psychology, for example, in researching cognitive capacities. And if you think about intelligence as a complex phenomenon, then you can see that even in very simplified models, how many aspects are coming together. And for example, at least these very complex abilities, characteristics are very well represented actually also in the playing of this game. And also these areas, these cognitive skill areas can be developed throughout playing this game. And if you are familiar with cognitive psychology, so mental rotation, that's a very basic measurement area where this cognitive abilities are tested, and also how this can be developed. But when you think about mathematics curriculum, even this basic connection is not so much played out, not so much implemented in mathematics curricula. Let's say so. So we had this intention to create this new. And if you think that you can combine this with technology as well, so this can be played also as a mobile game. So many aspects you can also measure with the technological instrument, and also it can help to have targeted information and feedback for learners, teachers, and parents. So this tool can be very useful in many areas. And not the last, it can be also make understandable or recognizable or experienceable that problem solving is fun after all. So we started to approach more systematically these cognitive areas. So you can see that how many aspects we started to systematically discover throughout the using of the game also in classroom context. And we started to work together with teachers, and also sort of cognitive sports events emerged from this work. So we had collaboration also with one of the largest cognitive sport event in the world, which is organized actually in China. And there are like 54,000 students are involved in this cognitive challenge in China. You can see the finals, and you can see that how Chinese students are playing the Mondrian blocks actually against a European team in a very friendly way. So it was a friendly finals there. It was a fun activity, but it's also nice to see that how far these children can get through getting immersed in these games on various ways. All right, let's move forward. So there is a Museum of Mathematics in New York where we opened actually the Mondrian year, the Mondrian 150th anniversary year with this game, and also other cognitive games, because of course Mondrian blocks is fortunately not unique in this sense. There are many, it's a unique game of course, but there are many other cognitive development games, and actually these have other connections to art and mathematics. You can see some publications where we explored also even a broader scale art and mathematics connections, and how to open mathematics curriculum towards art and towards design as well. So in South Africa, we had many projects in connection with this. There are children artworks are collected on a very large scale all around the world, where these connections are represented in maybe a more freer, more inspiring, more expressive format, where all these other intelligence types, let's say, so I don't like these categorizations, but other expressions of intelligence are also welcome in this format. There is a new book, it's coming in Finnish. It's about implementing non-formal methods in formal circumstances. So you can see this trend that informal education, out of school education is coming more and more into the school as well. And this is a very exciting process from the learning environment aspect. And this is a very, very fresh, it's a really hot book. It just appeared a few days ago. I will post these links in the chat. It's called Playful Learning in Early Childhood Education in Finland. This is actually the first English language handbook about Finnish early childhood curriculum as a full collection. And it also contains more than 100 activities, more than 100 games. So if you want to play cognitive development related games in your living room, or if any kindergarten teachers want to try these methods based on this collection, it can be done on a very simple way. And there are more tools also, some of them also included in this book. So there is the Logi Faces, another game, and it came from a designer, Daniel Lakos. You can see his portrait there, and he's also designing furniture, interior design, and you can see that this is a modular game as well, and it's about surfaces. So how it works, these are the modules, and these are the connections what you can make with these modules. You need to create a continuous surface. That's one of the basic play mode that gives one of the challenges, and you can see that architectural thinking and how this two-dimensionality enters into the spatial dimension. So the first dimension is added to this puzzle, and you can imagine also how many connections it can also develop. But this is also from the kindergarten throughout actually all levels of education, and we are really creating now a curriculum for this game as well. And you can see how this game is inspired, for example, furniture design, environmental design, how it became a stage scenery in a dance, contemporary dance performance. But because it's a three-dimensional shape, with working with visually impaired people, this is also very useful in their logical and cognitive development. So you can see many potentials. You can see also how Finnish teachers implementing this tool in different contexts. There is no time to go into these specific examples, but you can get an impression, I'm sure, based on these slides. That and here is a little bit spoiling the system. So there are only 3 levels of height in these modules, and this makes actually these combinatorial arrangements possible, which you can also approach as a matrix system. So Ioannis Saxon is the creator of another very remarkable game, Polyuniverse, and you can see this game which also contributed this methodology. These are all, by the way, free materials on these links. You will have these links also on the Academy webpage. And you can see also that how very serious scholars in the International Symmetry Festival, designers and mathematicians and physicists are playing with this together with the children, and also to go back to this DNS concept, building up mathematics and building up cognitive skills from early ages. This is a very important tool. We don't have time to really go deeper now in this, but there is also a study that how the patterns, the functions, and relations which are can be discovered through playing this game can contribute to the intellectual development and make new connections of this, developing their brain awareness of these children. And actually, if we also link it to the Finnish approach of early childhood education, you can see this diagram that how patterns, functions, and relations are in the center of these games in this age group, and how it contributes to develop analytic thinking, problem-solving strategies, mathematical, logical thinking, and reasoning, and how the connection of these various areas are made. This is one of my colleagues' study, Pia Parviainen from our university, writes very interesting studies in connection with this. You can look up more. And of course, this goes on in the primary school learning, where this more systematic areas of cognitive development and skill development are taking place. And you can see that this natural connection with other type of materials in textbooks as well. So, and there are many photos you can see about the diversity of these activities, what the single tool offer. And maybe I forgot to mention the most important thing. These modules started their careers as artworks. So
thank you very much, Kristóf. You offered us a thema con variazioni ad infinitum.
Yes.
It's wonderful to listen to your impressive activity, and we are so curious to follow you. Yes. Also. We have to meet again. Yes. So thank you very much. The questions are coming at the end. Thank you. And Ioannis, you have now. You have to unmute you.
Yeah, thank you, Kristóf. It's so interesting to see, you know, and I have many questions, but questions will follow, as Violeta said. Sure. Now we go to the second speaker of this evening, is Professor Kyriakos Efstathiou from Cyprus and Greece. Professor Efstathiou is a chair holder of the European Union of the European Research Area Chair on Digital Cultural Heritage project, which is called Mnemosini. From the memory in the Digital Heritage Research Laboratory, Cultural Informatics of the Department of Electrical Engineering and Computer Engineering in the Cyprus University of Technology. And also he's an emeritus professor of the Aristotle University of Thessaloniki, Greece. Kyriakos is an active and scientifically innovative and fruitful academician in fields of mechanical engineering and digital cultural heritage. His achievements are especially involved in research of implementation of digital technology and mechanical engineering in archaeology, a welcome example of this transdisciplinarity that we're doing here. Professor Efstathiou published many relevant and influenced scientific papers in journals of archaeology, manufacturing, and mechanical engineering. He's very active in establishing collaboration among scientists and institutions in Europe and some other countries in the world, and very active in innovative transfer of science and technology. He constructed accurate functional replicas of antique mechanisms from several archaeological excavations in Cyprus and Greece. For example, the Antikythera mechanism that we shall hear tonight. And he has also organized several exhibitions, and he's very active in popularization of science. With a Bachelor of Science in Mechanical Engineering from University of Stuttgart, Germany, and a PhD in the Mechanical Engineering School of the Aristotle University of Greece. He is a leader of the Aristotle University Greece research team, which investigates the Antikythera mechanism. Kyriakos is active during the last 5 years until today, and I would mention his co-authored interesting work in 2021 on the Antikythera mechanism, the proof of the accuracy of the astronomical calculations based on it in journal Heritage, and also in the Scientific Culture 2022 on the determination of the celebration of the next Pythian Games using the Antikythera mechanism, considering that they are celebrated uninterruptedly until today. I'm honored to have Professor Efstathiou with us. Kyriakos, the online platform is yours.
Thank you, Ioannis, for introducing me. Mr. President, dear Violeta, ladies and gentlemen, good afternoon. First, I want to congratulate Kristóf for his excellent presentation. And now I go direct to my presentation, which will be in an automatic way. Let me share my screen. Ladies and gentlemen, the subject of my presentation is the artistic complexity of the Antikythera mechanism. For those unfamiliar with the mechanism, allow me to give some general information about this subject. What was the Antikythera mechanism? The Antikythera mechanism was a technologically amazing analog computer, the first computer in the history. It was constructed about 2,200 years ago. It was used to calculate the diurnal and annual motion of the sun, the moon, and probably the planets among the stars. It implemented the astronomical knowledge of ancient Greeks about the motion of these heavenly bodies with astonishing accuracy, considering the anomalous orbit of the moon using a system of eccentric gears. The next mechanical calculators are built about 1,500 years later. At the beginning of the 13th century, the astronomical indicator of Wollendorf. 50 years later, the astronomical clock of Tondi, and in 14th century, the Prague astronomical clock, the same complex as the mechanism East. Later, in the 17th century, was built the calculator of Sicard, Kepler's collaborator, and the Pascaline of the great French scientist. But what could the Antikythera mechanism calculate? The mechanism was used to calculate the exact position of the sun, the moon, and possibly the planets in the sky. It calculated the phases of the moon, predicted eclipses, and indicated the start date of the Panhellenic Games, as for example, the Olympic Games. It contained a manual with detailed instructions. It had front and back doors with astronomical, geographical, and technological inscriptions covering much of the exterior of the mechanism. Similar ancient mechanism has not so far been found. Here we see a replica of the mechanism. The operator, by turning the moon pointer, gives motion to all the gears that in their turn rotated on the front side 2 pointers and on the back side 5 pointers. On the front side, there were 2 concentric circular scales. The outer scale had 365 subdivisions, the days of the year. The inner scale had 360 subdivisions and the names of the 12 zodiac constellations. At the backside of the mechanism were 2 spiral scales. The upper spiral consists of 5 windings with its total length divided in 235 sections corresponding to the 235 lunar months of the Metonic period. On these sections were carved the ancient names of the 12 lunar months and were repeated until all 235 months were completed. The lower backside dial is a Saros eclipse prediction dial arranged as a 4-turn spiral of 223 lunar months with glyphs indicating eclipse predictions. This is a transparent, educational, and fully functional model of the Antikythera mechanism in scale 3:1 constructed by our team. In the next video, we will see in the front side of the mechanism indications of the pointers of the sun and the moon during the operation of the mechanism. For example, at this position, at this state, we have a new moon. The moon sphere is black. At this stage, we have full moon. The sphere is white. Look behind the pointers. You see all the gears are moving. The operator, by choosing a date, can be seen the astronomical phenomena that occur on that day, or choosing an astronomical phenomenon, see when it will happen. The choice of the day 15th of June 2011, for example, results the following. At this day, the position of the sun on the sky is the constellation of Twins, and the corresponding position of the moon is the constellation of Sagittarius. At this day, we will have a full moon and possible a lunar eclipse. Whether this happens, we will see it by observing the pointer of the eclipses on the back side of the mechanism. Observing the pointer of the eclipses on the back side of the mechanism, we see that indeed at this day we will have a lunar eclipse. The Antikythera mechanism is the biggest technological breakthrough of antiquity worldwide. It is so important for the development of technology as the Parthenon on the evolution of architecture. Similar ancient mechanism has not been found so far. So, reasonable questions arises: what technical infrastructure there was the time of its construction, and what happened to the knowledge and the art it contained. In the Antikythera mechanism, 2nd century BC technologies are found which shift the history of technology back many centuries. Regarding the artistic complexity of the mechanism, I noted almost 20 sciences and arts which are involved in the construction, discovery, study, decoding, and reconstruction of the Antikythera mechanism. Sciences and knowledge involved in the design and construction of the mechanism in the 2nd century BC are astronomy, mathematics, geometry, engineering, metallurgy, manufacturing, geography, meteorology, knowledge of religious, social, and agricultural activities and traditions, and artistic design. Astronomy. We have a lot of evidence that the Greek astronomers knew they included in the mechanism astronomical calculations 2,200 years ago. The only accurate clock that the Asians had was the moon months. Meton connected the moon calendar to the annual one. He calculated that 19 years include 235 lunar months. Calibos, after 200 years, has calculated that Meton was making a mistake of 1 day every 76 years. These calculations are performed by the mechanism and appear on 2 scales at the backside of the mechanism. Aristarchus was the first astronomer in the history who talked about the heliocentric system and not Copernicus, as most people think. He calculated, among others, the size of Earth, Sun, and Moon. Hipparchus is considered as the greatest astronomer of all time. he lived in the time of the construction of the mechanism in Rhodos, where probably the mechanism was built. In order to understand the scientific magnitude of Hipparchus, I show you here one of his complex calculations. He calculated the transient motion of the Earth, which lasts almost 26,000 years. Another calculation of him is the determination of the distance between Earth and the Sun and Earth and Moon. In one of the few referrals regarding the mechanism, Cicero noticed that he visited the laboratory of Posidonios in Rhodos, where he admired a celestial sphere made by Posidonios. The knowledge of mathematics, especially of geometry, was necessary for the determination of the number of the needed gears with their size and number of teeth, and for the design of the gears and other components of the mechanism, like the dials, especially the two spiral scales at the back side of the mechanism. In order to be able to write the names of the 235 lunar months on the Metonic dial, the circumference of a large diameter circular scale was needed. It is remarkable how smart they solved this problem. Instead of a circular dial, they designed a spiral one. The question is whether these were Archimedes spirals or spirals consist of two semicircles. We have proved that they are spirals consist of two semicircles. Existence and interconnection of knowledge in mathematics, physics, engineering, and astronomy during the Hellenistic era. All of you know the names Euclid, Archimedes, as well as the astronomers Aristarchus, Eratosthenes, and Hipparchus. In this slide, I want to show the interconnection of knowledge and the cooperation between them. The knowledge, for example, of Euclid's geometry was an essential tool for astronomers. Although it sounds strange, the scientists of the Hellenistic era communicated and collaborated even if they lived in different cities and states. A typical example is this part of a letter of Archimedes from Syracuse in Sicily to Eratosthenes in Alexandria in Egypt, where he wrote to him, "I have previously sent you some of the information I had received, listing the uttering them and telling you to try to find their proofs which I had temporarily not announced." Metallurgy was necessary for the creation of the metal alloy, a copper tin alloy, and the production of the necessary materials for the construction of the various parts of the mechanism. Engineering knowledge, especially mechanical engineering knowledge, is self-evident that it was necessary for the design of the mechanism. Manufacturing was necessary, of course, for the construction of the various parts of the mechanism. A question arises: did the Greek engineers and technicians have the knowledge and the abilities to build the mechanism 2,200 years ago? I will give you some very brief facts that prove that they had these abilities. Until the discovery of the Antikythera mechanism, the construction of the first real gears was stated centuries later. The gears of the Antikythera mechanism are the first in the world history. Pappus of Alexandria described several machines which included gears that were described by earlier mathematicians and engineers such as Archimedes and Heron from Alexandria. We see in this slide some of these machines. Two examples that show the abilities of our ancestors in the area of mechanical engineering and design. The first one is shown here. The date scale of the mechanism had the shape of a ring. The ring was removable. Under this date ring, there were 365 holes. Every 4 years, the operator was able to remove the ring and move it 1 hole to take leap years into account. The second example is shown here. We see the metonic scale in the form of a spiral consisting of 5 turns. But how is the corresponding pointer of the metonic scale designed? It follows the spiral exactly like the tip of a record player needle. The best proof that the ancient Greek engineers and technicians had the knowledge and skills to design and build the mechanism is the mechanism itself. In this diagram, you can see the gear trains and the connections between the cooperating gears with a number of teeth of each gear, which shows the complexity of the structure of the mechanism. Manufacturing. Here we see metallic axes and shafts of complex geometry found in the mechanism. For their manufacturing, as well as the manufacturing of metal plates like this, machine tools are required, as well as corresponding steel cutting tools. We found references in the ancient literature that refer to their existence and use. Geography and meteorology. The date pointer of the mechanism refers to texts engraved on the surfaces of the mechanism with geographical and meteorological information. For example, I highlight here 2 positions from the backside dials of the mechanism in which specific winds with their direction are mentioned. Knowledge of religious, social, and agricultural activities and traditions. In the next 2 slides, I will show you 2 examples that indicate the need for this knowledge for the design of the paradigma and for the design of the Pan-Hellenic Games dial. Here we see the first example, the paradigma. The paradigma shows the rising or sinking date of some brilliant stars. These phenomena appear every year at a fixed time in the sky. Such phenomena shows us the paradigma like this one. Hesiod mentioned that the harvest period begins on the day it will appear the constellation of Pleiades for the first time in the sky. And here the second example, the dial of the Pan-Hellenic Crown Games. Sciences and knowledge involved in the discovery, study, decoding, and reconstruction of the mechanism in the last 100 years. Regarding the study, the coding, and the reconstruction of the mechanism nowadays, it's obvious that the use of the sciences and knowledge I mentioned before and are shown on the left of the slide was also necessary today. Apart from these, also these shown on the right part of the slide were necessary. Archaeology, underwater archaeology, physics, chemistry, history, epigraphology, navigation, philology of ancient Greek and Latin, and specialized new technologies like tomography and PTM technology. Archaeology and underwater archaeology. In 75 BC, a large Roman ship paddled with the waves on the Rao Sea between the mainland of Greece and Crete. Finally, the boat sank on the shores of the small Greek island Antikythera. The ship was loaded with works of art and other precious artifacts. 2,000 years later, around the Easter of 1900 AD, spunk divers from Simi by chance discovered the shipwreck. A year later, the Archaeological School of Athens made the first large-scale marine excavation. Here we can see some of the found objects that are in the Archaeological Museum of Athens, like this statue, or the philosopher, the famous teenager of Antikythera, this glamorous cap, and these earrings. Among the findings was the Antikythera mechanism, which after 2,000 years on the ocean floor was broken, corroded, and petrified to change the knowledge about the technological capabilities of our ancestors that we had until now. Here we see two of the fragments of the mechanism. Chemistry and metallurgy are necessary for the chemical analysis of the material used for the construction of the mechanism, and today to choose corresponding material for its reconstruction. History and epigraphology. The necessity of historians is obvious. Regarding the epigraphology, this was used to estimate the date of the construction of the mechanism. The epigraphic researches carried out for the study of the types of letters of the text in the fragments of the mechanism showed that the Antikythera mechanism must have been constructed approximately between the second half of the 2nd century BC and the beginning of the 1st century BC. That means between 150 and 100 BC, with an error of plus minus 50 years. Geography and navigation. Knowledge on geography and navigation, combined with history knowledge, were necessary to determine probable courses of the ship sunk on the shores of Antikythera. Relevant studies have shown that the most likely course is the one shown here. The ship started from the eastern Aegean, probably from Bergamon, with stops on various islands, such as Rhodos, and then headed west, traveling north of Crete and south of Peloponnese. It sank between Peloponnese and Crete. The usual course of these ships continued north along the coast of western Greece to the High of Corfu, and from there southwest to Syracuse, with a final destination in Rome. Philology of ancient Greek and Latin. Knowledge on philology of ancient Greek and Latin was necessary for researching ancient Greek and Latin sources for information related to the mechanism. Here, two examples of Greek bibliographic sources. The term spherobeia in this text refers to the construction of Uranion spheron, celestial globe or sphere, like the Antikythera mechanism that describe the movements of celestial bodies in the sky. The text also refers to Archimedes. Here, some Latin sources. The most known reference to celestial spheres is made by Cicero, who also mentioned Archimedes and the astronomer Posidonius from Rhodos. In order to be able to see the internal parts and features of the fragments of the mechanism, as well as to read the engraved on the fragments text, specialized new innovative technologies were used. Here we see all the found fragments of the mechanism. PDM-DOM's innovative digital image capture mechanism, an advanced photography for reading text, made possible the reading of also captured, faded, and worn inscriptions and other details on the surfaces of the fragments of the Antikythera mechanism, even if they were not visible with the best systems of conventional and digital photography, as for example, the text on the fragment 19 we see here. Microfocus X-ray tomography. Here we see fragment A, the largest of the mechanism inside the tomographer. Sample tomography results. Looking at the tomography of fragment A, we can see here the different elements contained in this fragment. If we choose only the density of copper, we have these results, and it's very easy to identify the various elements, gears, and shafts included in this fragment. Some more topography results which help to find out how was the moon pointer controlled. In fragment A, at this point, is a gear with 223 teeth. Nearby, there are two gears with 50 teeth each. What was their use? We see here two tomography sections. The second one is 2 millimeters deeper in relation to the first one. In reality, we do not have two gears as we imagine seeing the outer surface of the fragment, but 4 gears, where the 2 more gears shown on the left of the slide are below the first 2.
Here,
all the 4 gears of this.
The time is over, dear Kyriakos.
After gear K1,
only 2 minutes.
The slot is mounted eccentric in relation to the gear K2 with a pin, and is driven from it by means of a pin. During the rotation of the gears, due to this eccentricity, the radius of the contact point of the pin in the slot changes, while the angular velocity of the lower gear K2 is constant. The angular velocity of the upper gear K1 is variable. This variable angular velocity is then transmitted to the axis which rotates the pointer of the moon. Here we see the whole system, which consists of 6 gears. This movement simulates the actual anomalous lunar motion with an accuracy of 1 to 400. It is indeed the simulation of Kepler's second law. The tomographies helped a lot to the redesign of the mechanism. Here we see the design gears and shafts and their correlation with the real ones found in the fragment A. Using the tomography of the fragments, the various elements contained in the fragments were identified, and on the basis of these results, the mechanism is redesigned and accurate functional replica of it are constructed. And here you see how we redesign the whole gear chain of the mechanism. The model had 19 shafts, 39 gears, and 8 pointers. Combining good engineering knowledge with artistic design capabilities, the ancient Greek managed to build a functional mechanism in the smallest possible dimension, which at the same time is something as beautiful as jewelry. Here you see an accurate replica of the mechanism. As I mentioned before, the mechanism is not only very complicated, as you can see at the same time is something as beautiful as jewelry. Conclusion. The artistic complexity of the Antikythera mechanism is very high. In order to be able to build it in ancient Greece, knowledge and skills were combined in the following subject areas: astronomy, mathematics, geometry, engineering, metallurgy, manufacturing, geography, meteorology, knowledge of religious, social, and agricultural activities and traditions, and artistic design. In order to be able to decode the mechanism and rebuild it 2,200 years after its first construction, additional knowledge was needed in archaeology and underwater archaeology, physics and chemistry, history, epigraphology, navigation, philology of ancient Greek and Latin, and the use of specialized new technologies like tomography and PDM technology. Okay.
Thank you. Thank you, Kyriakos. Thank you. Many questions, I suppose, ready to be, presented to you in due time. Now, I would like to ask Violeta if there is any questions for the first speaker. But taking the privilege of being moderator, I would like to be the first one, if you allow me, please. So, Kristóf, I would like to answer the only one question. You presented an interesting STEAM, as you said, presentation, but only for kindergarten or primary school. What about secondary or school or higher education? Can you?
Thank you a lot, Ioannis. In fact, secondary school was also part of the presentation, but due to the shortness of time, I went already over time, so I couldn't really go into that. but it's absolutely part of it, and also higher education as well. Yes, so we implement these methods also in higher education and secondary school, of course.
In a respective level, of course, of difficulty, etc.
Yes, exactly.
Okay, thanks.
Complexity.
Violeta, you can.
Yes, thank you very much. Thank you very much. First, I have Peter Hermann and Bounty Stassos. They would like to ask you, Kristóf. So first is Peter Hermann. I don't know if you've read already. Can you say something of the different aspects and their relation? First, perceived environment. Second, active engagement with the environment. And third, relating with others. Please, Kristóf.
Yes, this is a very, very good question, a very tricky question also, because it's really go into the hit the middle of the whole problematics. Actually, if you think about the concept of motivational engagement, as the professor mentioned, engagement, that's a very complex concept, and to measure it, we always or many times focus on this the performance and academic performance is studied, but what about, for example, the school climate? I think this is what is coming from the perception of the environment, and also with the complex social relationships which are also affected by this corresponding circumstances what are hidden in this question. So I would say, like, the school climate, or this is what I also try to highlight with this creative ecology when I used this term, where these complex relationships come into play. And there are already some studies which are focusing especially on these contexts. So thanks a lot.
Mm-hmm. Thank you very much. So before our president has also a question, but before it was Tassos Mountains. Tassos, may I ask you, may I please invite you to put, because he was writing in the chat. Hello, are you with us, Tassos?
Yes. I will ask the two questions quickly. My first question is to Kristóf. Since this role has started from the 60s, as you mentioned, with DNS and so on, I wonder what is the feedback of the success of this approach, how it has developed over the years. What do you know from the people who followed it? And how has it affected their lives, so you can do better things today?
Yes, actually, it starts much earlier, of course. If you think about Fröber's gifts, for example, who really emphasized from the kindergarten age, or Montessori pedagogy, and also from the philosophical side, Dewey is always mentioned and always referred. And actually, we can see that these methods, that's what I try to highlight, that these methods are now coming to the classrooms in many educational cultures, and there are many discussions about this, and also many research is measuring the different aspects of these methods. But as also it was highlighted the previous question, this is a very complex issue and depends on many variables. So it's hard to say that what is good, what's not good in general, but there are more the cases what is telling to us.
Okay, thank you. And my second question concerns the concept of infinity. Everything you have there and the children play with is a finite, is a number of blocks that have to be combined and so on. But the students, and mathematics especially, would like to ask, what happens if we count in larger and larger numbers, if we cut something in smaller and smaller pieces? And there are paintings of Mondrian that I spoke about also in my lecture here in the academy, which have infinitely detail, very small detail of flowers. Isn't that idea at all treated or handled in STEM?
That's an amazing question as well. So if you think about tessellation, right? So also when you discover periodicity, and you can also discover aperiodic tessellation, and these are like glimpses of the infinite in our limited world, and this is also like this expectation shock, I would call, that the surprise comes when someone starts to understand, or not understand, but perceive that this can be continued really without any end, and this is how these activities sort of give a very tiny glimpse into this infinite
So you
universe
have
and
come
the
across
infinity
this question.
concept. Yeah, but you are right. It needs to be. This is what I also try to call this brain awareness, and that we are reflecting on what we are doing. It's not just the activity. It's not learning just to do the activity, but it's more the learning comes when you start to reflect on what you are doing.
Thank you very much. So please, President Professor Mainzer.
Yeah, bringing the question of Tassos, the last question, to the point. That was done by Hermann Weyl, by the way, who defined mathematics is the science of infinity. That means it started with infinity. That's quite right. Now, my question is, I'm wondering, nowadays, the discussions of AI and artificial intelligence, things like that. Now, what is the main difference between human cognition and intelligence and AI and digital computer nowadays? I think you highlighted that. That is, human intelligence is embodied. That means it is not only formal logical thinking, but intuition and even sensors, our hands, embodiment, embodied mind. I think that is the crucial insight of modern cognitive science, and that is even true for mathematics. Now, my question is a little bit on the line of what was asked by Ioannis, namely the Mondrian games are mainly considering applications for the elementary schools and training, the combination of embodiment and mathematical geometrical thinking. What about, are there inquiries, even empirical analysis of the influence of embodiment in high mathematics? That means how much are working mathematicians are influenced by this kind of intuition, quite contrary to the computer nowadays. Are there empirical results in educational science?
Fantastic insights are opening here, because also the combination, you are also sort of connected these two talks, because I think in this Antikytheran mechanism, we could see that how a very, very complex mechanism is working and helping us to have new insights and understanding of processes around us. But indeed, the human intelligence and also the organic learning and intelligence is not a combination only of very complex mechanisms. It's very important, I think, that at least these mechanisms are that complex that we cannot call them mechanisms. That's why inspiration, imagination, these are not mechanical type of processes. And actually, your question, sorry, about the studies. Yes, there are studies about this origin of mathematical concepts and how the embodied physical conditions also lead the mind to these discoveries. And there are certainly, it would be a very good idea to study the higher mathematics connections with this. I'm not aware of these studies actually, but in the field of education, there are a lot of studies about embodied learning. That's a very important field, and also we have also many kind of tools and many kind of insights can be collected about embodied learning, but certainly the idea what you write would be very worth to see more. Thank you.
Thank you, Ioannis. Do somebody would like also to?
Somebody for the second speaker, I mean? Yes. For the second speaker, for Professor Efstathiou, is there any question? No? Okay, so...
There is a comment, if you see the chat.
Yeah, there is a comment. Kyriakos was particularly regarding ancient technology. I think such devices have too a strong background in Hellenistic Alexandria.
Yes, I agree.
Yes, that was my question, not to steal from your time.
Thank you,
I
Denise.
did it in writing, so thank you for the presentation.
Thank you, Denise. So thank you, all of you, for your presence. And I would like, Violeta, you to close this colloquium and say bye-bye, good Easter, and next.
Oh,
please, Violeta.
You can imagine, I would like to ask also and ask again. We are both so happy to have this possibility to meet from all over the world, and we shall continue it in October. I already received so many questions from interested people who ask why such a long time with any colloquium. So, but we spoke, and Ioannis also had the idea just to enjoy now a long time, wonderful summertime. Anyway, we are so happy to have you. We stay in contact. If you desire to to come in contact with our lecturers, please do write us and do look in the internet in order to discover again and again. Thank you so much. And thank
Violeta,
you
excuse me.
Yeah.
Excuse me, Violeta. I don't know if you can see what I have in my hand here.
Oh,
Yes.
I
I
suppose.
Yes.
Wait a minute. Do you see it?
Oh,
Ah.
nice.
Oh.
Beautiful.
This is a miniature replica of the mechanism. This is the front side, and wait a moment, and this is the back side.
Does it work? Does it work?
No. It's not possible. I said in my presentation that the Antikythera mechanism is built, is the smallest dimension that can be functional. If we make it smaller, it does not work. This is accurate model in scale 1 to 3, accurate regarding the outside surfaces, inscriptions, and all this.
Right.
I
You can
congratulate.
find it in the internet. Our team make it, and you can buy it in the internet if you want.
Oh, this is wonderful. Please tell me exactly, send me exactly the address where it's
I
possible.
will send the link to the website.
I must tell you, it is not the first time I listened to you. We met again, you remember, and you
Yes, yes.
presented. I have an existential feeling of this. It is incredible. It's just being in, to see the correspondence with so many thousands of years and such an incredible.
Actually, I would like to add, Violeta, that we have a project, but still working with you. You say
I have already ideas.
about the Antikythera mechanism and music.
Yes, but you know, the both presentation today, it was like a performance for me. It was
Exactly.
like a piece of art. And when you did not want to understand the scientific aspects and you just look at what happens, as I told you, I have the feeling of a performance. So this is so inspiring. And I suppose you have this similar reactions as I have. I do not find the words. We need the music.
Okay.
Thank you very much. We stay in contact all over the time. And who knows, maybe we just improvise a colloquium in the middle of July or August.
I don't.
Because it's true. We are longing then.
Okay.
Thank you very much.
Okay.
Best
Bye-bye.
health and happiness. Bye.
Take care. Thank you very much to all of you. Thank you.
Thank you.
Thank you.